Thank you for joining this webinar to learn about how to supercharge your LC method development. My name is Scott Bollen and I'm one of the business development managers for Agilent LC columns. And today I'm happy to share with you how a new column from Agilent, the Supercharge Infinity Poroshell 120 CS-C18, can speed up your method development and be used to create highly flexible and easily transferable LC and LC-MS methods. Here is a quick overview of this presentation, which will focus on fast, simple, reverse phase LC method development. First, I will discuss formic acid in LC mobile phase options and consider their instrument and column compatibility, as well as which options are the most universal. Next up will be flexible column choices and how the right phase on a superficially porous particle can speed up method development, leading to fast, universal, compatible methodology. Of course, we all know that method development is not always easy and doesn't always go as planned, so I will also discuss some options for what to do if the universal approach does not work for you. And finally, I will wrap up with a few conclusions. So let's get started. The first thing you should do is organise your thoughts and define your method objectives. Before you start with the actual method development experiments, you should ask yourself a few questions. How many peaks are likely to be present? Is it going to be easy or challenging to separate those peaks? If challenging, this may require small particles or longer columns. So then you need to consider if efficiency or speed is more important. Small particle columns can help with speed. If you are running hundreds or thousands of samples, speed will be very important. On the other hand, if you're looking at just a few samples a week, speed may be less of a concern, and longer columns may work better for you. Also, consider what kind of instrumentation is available. Can you run gradients? Can you run pressures above 400 bar? Is that available to you? Who is going to run the routine samples and what is the level of their training? Sub 2 micron columns are great for fast methods, but are definitely more challenging to run and require high pressure instrumentation. All of these questions and certainly others can help you decide on the requirements of the method you will develop and what sort of column configuration you should pursue. There are several reasons that analysts desire to use formic acid as an LC mobile phase. First of all, it's easy, very easy in fact. Simply dilute 1 ml into 1 litre of water and you're good to go. If using high purity solvents, filtration is often not even needed, unless of course you're using a very low particle size LC column. It is also compatible with pretty much every LC column. The pH is only about 2.8, which is nice and acidic, but not so low that it will compromise column lifetime. And of course it works well with LC-MS detection. Not only is it compatible, but it aids in ionisation and will not cause signal suppression and ultimately can improve LC-MS sensitivity. Formic acid also is easily soluble in both water and organic. Having good solubility in organic also allows you to add your mobile phase modifier to both bottles. This is important for gradient analysis to ensure that you maintain a constant ionic strength across the gradient, which will contribute to method robustness. Now let's look at a few chromatographic examples of these benefits with formic acid mobile phases. Here is a simple sensitive robust analysis of glyphosate and a few related compounds. As promised, this method uses a simple formic acid mobile phase with a methanol gradient and it reliably detects 10 ppt glyphosate with LC-MS and MES detection. A few other selling features of this reverse phase method is that sample preparation is also easy, with no derivatization in this case needed. And because glyphosate is known to be a metal sensitive compound, peak shape and sensitivity are improved for the use of a peak flow path and adding the Infinity Lab, the activator additive to the eluent. Agilent supplies most of its columns now in peak hardware, which is very, very good if you do have sticky compounds. I should also note that this separation is accomplished on the new Agilent Infinity Lab Poroshell 120 CS-C18 column, which I will tell you more about later. You can see the robustness and sensitivity of that glyphosate method here. The minimum detectable limit, or MDL, for glyphosate is calculated on 4 different lots of column material and is consistently under 10 ppt, thanks in part to that simple formic acid mobile phase. This method is proven to be reproducible and consistent on both older and brand new CS C18 columns. Of course, formic acid is not the only LCMS compatible mobile phase. This slide shows a comparison of beta blockers separated with formic acid and with ammonium formate buffer, which is also considered an LCMS friendly mobile phase, as it is also volatile. However, we can clearly see that formic acid gives better sensitivity and signal to noise calculations for all 6 beta blockers compared to the ammonium formate separation. This is because the salts from the buffer still contribute to a small amount of ion suppression compared to the weaker ionic strength formic acid mobile phase. Not only is formic acid mobile phase easy to use and sensitive, but it also is compatible with a variety of modes of detection, shown here with both UV and MS separation of antidepressants. The simple mobile phase works well with both instrument configurations. Also notable, the separation is performed on a 2.7 superficially porous particle, which keeps the pressure low while maintaining high performance. Together, this combination of a simple mobile phase with superficially porous particles makes for a high performing and highly flexible method that can be easily achieved on a variety of instrumentation, regardless of detectors or pressure limitations. Of course, there are a few challenges with formic acid mobile phases as well. It is volatile, which helps with LCMS, but also means it can evaporate and change concentration while it sits on your instrument, if not properly sealed. It is acidic, so retention of basic analytes in reverse phase mode may be low. Speaking of basic analytes, formic acid is also low in ionic strength, which may lead to poor peak shape for bases. The good news is that there are a couple of column bonded phases that can help avoid this. Also, charge analytes, both acidic and basic, may experience some initial retention time drift on new columns. There is help here too, as column conditioning can bypass this. Let me show you some tips and tricks for how to be successful with your formic acid mobile phase. I mentioned the volatility of formic acid as a potential concern. These stay safe caps can help. While their original intention was to keep solvent vapours out of the lab for your safety, they also have the added bonus of significantly slowing evaporation of your mobile phases. The caps are sealed but vented, so you can be sure that your mobile phase composition isn't changing over time. And the handy time strip tells you when you need to change the filter. These caps will fit on most mobile LC phase solvent bottles, but we do have ergonomic Infinity Lab solvent bottles that make it easier to fit more bottles in your solvent tray, which is great for method development. And they also are much easier to handle due to the narrow bottle design. I know that I've personally got that entire table of mobile phase options sitting on top of my LC. Here you can see the potential peak shape issues for basic compounds with formic acid. This is a separation of tricyclic antidepressants, which are now well known for their troublesome peak shape on a traditional C18 column with the formic acid mobile phase. These compounds often tail, but in this case you can see they are broadened and splitting. However, if we use the appropriate column bonded phase for this situation, we can overcome the peak shape concerns. The Infinity Lab Poroshell 120 CSC18 is designed just for this. It provides good basic compound peak shape with low ionic strength mobile phases like formic acid. Of course, there is nothing wrong with the traditional C18 column. Its performance can be improved if it's used with a more appropriate mobile phase, as shown here. Using TFA allows the peaks to sharpen, and if we look at the plotted peak widths on the right, we can see that it's now performing similarly to the CSC18. However, TFA is much less desirable mobile phase. posing compatibility issues for some columns and some detectors. Its extremely low pH can compromise column lifetime for many phases, and it also contributes to significant ion suppression with LCMS detection. I also mentioned that you may see some retention time drift when using formic acid mobile phase. You can see that here in this plot. The sample contained basic and neutral analytes under isocratic condition with a 0.1% formic acid and acetonitrile mobile phase. Repeat injections were performed on a brand new column. As you can see, the two basic analytes in orange and green here showed slight retention loss by about 5%, while the two neutral compounds in blue remained fairly constant. This experiment was performed on a superficially porous charged surface column. If we look at two other traditional end-capped and non-end-capped C18 columns, you will see the exact same pattern. And finally, if we look here at a totally porous particle with a charged surface, you will see the same pattern as before. This is the nature of working with charged analytes in a simple formic acid mobile phase. All columns do this. The good news is that the drift is subtle and it levels out fairly quickly. To be proactive, you can condition a new column to avoid that retention time drift altogether. Here you have the same plot from the previous slide, but an acidic analyte was also added in, which actually gained some retention over time. However, if you condition a new column for a couple of hours and repeat the experiment, you can see that retention times are now much more reproducible. This procedure only needs to be done once when the column is brand new right out of the box. Occasionally longer conditioning periods may be preferred for really long columns. These are 50 ml ones shown here, or for acidic analytes which drift slightly more than basic analytes as seen in these plots. If you are curious what that drift looks like chromatographically, here is the data from those same scatter plots. Without conditioning, you can see the acidic peak, peak 2 here, shows a little movement, as well as the next two peaks which are bases. All while the last two neutral peaks remain pretty stable. And of course, with the conditioned column on the right, retention times are very reproducible from the start. And here is some data to reassure you that the conditioning only needs to be done once. This is the first set of injections on a conditioned column. That column was stored in acetonitrile for 5 weeks and then retested. And now if I overlay the two data sets, you can see perfectly reproducible retention between the two experiment sessions. So nothing is lost while the column sits in storage. For this discussion of formic acid, you should also be mindful of how to store your reverse fade columns. If you store columns in formic acid mobile phase, retention times may shift, and even water has a small effect. But if the column is stored in pure acetonitrile, it will be reproducible time after time. So please always store your reverse phase columns in 100% acetonitrile. So now let's have a look at an approach to the method development. By now you have determined the best mobile phase to retain and separate your compounds, and also something that is compatible with your instrument and your desired mode of detection. Hopefully something simple like 0.1% formic acid in water with an acetonitrile gradient shows promise for your separation. Now let's take the next step and screen a few columns to see which gives the most promising results. Selecting 3 or 4 short high efficiency columns is a good starting point. With modern columns you can do this step fairly quickly. When I say modern columns, I mean high efficiency particles. This can mean traditional totally porous sub 2 micron particles, or it can mean superficially porous particles. Sub 2 micron particles can generate a lot of pressure and therefore aren't compatible with all LC systems. Since our goal is to take a flexible, universal, compatible method, let's focus on a superficially porous particle, like Agilent's Poroshell 120. Poroshell particles are made of a solid core with only a porous outer layer, so the analytes only move through the shell of the particle, creating a much more shorter path for diffusion and therefore a narrower, more efficient peak compared to their similarly sized totally porous particle counterparts. Because of this difference in particle morphology, a 2.7 micron Poroshell particle is able to get about the same efficiency as a traditional sub-2 micron particle. Of course, the larger Poroshell particle size means that you get the same performance but at half the pressure, which allows much more flexibility with LC instrumentation. Here is an example of how high efficiency columns like Poroshell 120 can speed up your method development. On top is a method on a traditional totally porous 5 micron particle Zorbax column. It's a 35-minute method, so quite a few hours would be spent screening multiple columns of this dimension. Below is the same method with properly scaled gradient and flow rate run on a Poroshell column. It's a shorter column, but with the smaller particle size and superficially porous particle, it gives you a more efficient analysis with the same results in about 1/4 of the time. You'll also notice that it still operates at a pressure that is compatible with most HPLCs. When you are considering Poroshell particles for your method development, there are 3 particle sizes available. 1.9 micron is best for UHPLC systems. They are very efficient but generate higher back pressures. 4 micron is best for updating legacy methods that are run on 5 micron totally porous particles. You will get twice the efficiency with no pressure gain for similarly sized columns. And 2.7 micron is the best column particle size as it is the most flexible. As I mentioned before, they achieve similar performance to sub-2 micron columns at half the pressure, which makes them ideal for UHPLC-like separations on HPLC instruments. Here are the 19 chemistries currently available on Poroshell 120 particles, all of which are available on the flexible 2.7 particle size. There are general purpose columns, low and high pH phases, chemistries designed for alternative selectivity, phases for polar compounds including Hillic, and also chemistries intended for chiral separations. This can be a little overwhelming to look at, so I want to highlight one particularly flexible phase. The new charged surface CS-C18 Poroshell column. The Infinity Lab Poroshell 120 CS-C18 is built from Agilent innovation. It uses a hybrid NCAT C18 phase which is high pH stability and offers unique selectivity. On a superficially porous particle with a positively charged surface, the 2.7 micron Poroshell particle allows for higher efficiency at lower pressures, and the charged surface enables better basic compound peak shape with simple low ionic strength mobile phases like formic acid. Remember, basic compound peak shape was one of the cons with the formic acid mobile phase, but this column chemistry now solves that problem. Altogether, this makes a highly flexible LC column that is compatible with a simple formic acid mobile phase on any LC instrument with a variety of detection modes. For added column flexibility, this column is also available in peat-lined stainless steel hardware to improve the analysis of metal-sensitive compounds. It should also be noted that the pH of this can be used at very high pH range as well to play around with the charge on the column. Adding the CS-C18 to the Poroshell 120 portfolio brings the total number of C18 phases to 4. Let's see how they compare and consider when to use which Poroshell C18 phase. Perhaps you will even screen all of these phases as part of your systemic method development. The EC-C18 is still our best general purpose column. It gives good peak shape for most compounds. The stable bond C18 offers excellent low pH stability for use with mobile phases below a pH of 2, so when you need better retention of acidic analytes. An HPH C18 has excellent stability and good lifetime at high pH, which gives good improved retention for basic analytes. The CS-C18 offers both low and high pH mobile phase compatibility, with the added benefit of improved basic compound performance with low ionic strength mobile phases like formic acid. All 4 phases have unique selectivity, with CS-C18 being the most different of the bunch due to its charged surface, giving a different orthogonality. Here is a selectivity comparison of the 4 Poroshell 120 C18 phases using a sample of veterinary drugs. This is an example of a systemic column screen that you may do during your method development. Each of these phases is run using the same simple formic acid and acetonitrol gradient. As you can see, each C18 phase produces a slightly different separation, with CS-C18 giving the most unique result. And in this case, the CS-C18 is also the most promising separation, with the best minimum resolution of the 4 different compounds. From here, maybe a longer column or a slightly shallower gradient would lead to baseline resolution of all analytes on the CS-C18. This example was pretty simple with only 9 analytes. What if your sample is more complex, like this separation of 25 pharmaceutical compounds? This separation is performed using LCMS, so baseline resolution of all analytes is not absolutely necessary, but it can still help to avoid issues with signal suppression. And occasionally LCMS is not even enough when you have structurally similar compounds that may produce a signal for the same mass charge, such as isobaric compounds. Let's try to simplify this column comparison by breaking this mixture down to smaller classes of compounds. Maybe this will make the best column choice more clear. First, let's look at some benzodiazepines. There are 6 in that 25 compound mixture. Each phase yields different results. CS-C18 has close solution of peaks 2 and 3, while peaks 3 and 4 elute closely on EC and HPH-C18. I can't honestly say one of these separations is better than the other, just that they are different. However, stable bond C18 is clearly the worst performer of this specific set of results, with peaks 3 and 5 co-eluting completely. What if we look at a set of phenylethylamines in that same sample? Once again, 4 different C18s produce 4 different results. This time the biggest differences can be seen in peaks 2 and 3. Methamphetamine and MDA. These 2 compounds co-elute on 3 of the 4 phases, while CS-C18 is the only one capable of chromatographically resolving them. And finally, how does the separation of opioids compare? Now the critical pair is peaks 4 and 5, meperidine and heroin. This time, CS-C18 is the only phase that does not offer baseline resolution of these compounds. As you can see, the more complex sample mixtures get, the more difficult it may be to choose the best column for the separation. Each phase you screen may offer some good points and some less desirable ones. So maybe it's time to consider method quality metrics over the resolution, like peak shape or sample capacity. This is a typical loading capacity curve for 4 columns. The Poroshell CS-C18 is in blue, a traditional NCAP C18 is in orange, a traditional non-NCAP C18 in green, and a totally porous particle C18 is shown in red. The x-axis is a logarithmic scale of the amount of amitriptyline loaded on to the column, while the y-axis is the plot of peak widths. When loading is low, you can see that all columns perform similarly, with narrow, sharp peaks. However, as we inject more sample onto the columns, peaks begin to broaden, which can cause a loss of performance and resolution. The largest differences in performance happen at high sample load, and you can see that the blue CS-C18 curve stands out from the pack by maintaining relatively narrower peaks and higher performance throughout the loading experiment. Here you can see what the loading capacity data looks like chromatographically. These are the same 4 columns from the plot in the previous slide. At moderate sample load, you can see where the performance starts to differ for the charged surface C18. It has a narrow symmetrical peak, while the other 3 traditional C18s start to tail. And at high sample load, you can see the severe peak broadening that occurs with the traditional C18s. And while the CS-C18 does also tail when overloaded, it is not nearly to the same extent. The sample capacity improvements demonstrated on the CSC18 offer significant benefits to impurity analysis such as this one. This data shows a concentrated sample of amitriptyline with two impurities, A and B, at 0.25% by weight on the Poroshell CSC18. You need to inject larger volumes of sample to get a strong enough signal to reliably integrate and quantify those smaller impurity peaks. However, as you inject more sample, the main peak will overload and broaden. This is not a problem on the CSC18, as you see here. It easily maintains resolution for all three compounds. But if the same experiment is performed on a traditional C18, the story is a bit different. Now, as more sample is injected to improve the impurity signals, amitriptyline significantly broadens and its retention time shifts in, consuming the first impurity peak A. You may also notice that impurity peak B is impacted by the significant tailing of amitriptyline and never forms a sharp peak on the traditional C18 column. You are now on the home stretch for your systematic method development. Hopefully all that's left is to fine-tune your separation. You started with a generic gradient, looked at organic modifiers and pH, and evaluated different columns across wide ranges of selectivity. At this point, you should have a pretty good separation with adequate resolution and good peak shape for your target compound. In some cases, you may want to optimize the method to see if you can make it shorter. Faster runtimes mean you can get your analysis done faster and move on to other interests. You may also take a look at your separation at different temperatures to see if you can fine-tune the separation and resolution even more. Overall, you can be confident you've developed your method quickly and in a thoughtful way to improve your chances for a more robust, reliable method. Throughout this presentation, I have reviewed a logical stepwise approach to speed up the LC method development. The majority of the chromatographic examples shown have featured the new Agilent InfinityLab Poroshell 120 CSC18 column with a simple formic acid mobile phase. Formic acid as your mobile phase modifier means that your method will be compatible with a wide variety of instrument and detector configurations, including LCMS. Formic acid also gives excellent LCMS sensitivity, as we saw for the glyphosate application earlier. The CSC18 is bonded to a very flexible 2.7 micron superficially porous particle. This gives you high efficiency at pressures suitable for all LC systems. Combining formic acid and the CSC18 column offers a universally compatible method that can be run on any LC system without the need for additional method development. And while not really covered in this presentation, don't forget that I mentioned those peak line columns that can offer additional benefits for metal sensitive compounds too. And by now, some of you are probably thinking all that was discussed was a C18 column with one mobile phase option. What if that doesn't work for me? Which is completely fair. There's no one size that fits all when it comes to method development in LC. More challenging separations will require more creative method development options. That is why we have 19 chemistries on Poroshell 120, each with unique selectivity and all with the performance and pressure benefits of superficially porous particles. 12 of these phases are for reverse phase LC separations, with several being very orthogonal. If C18 columns are not working for your separation, this is where you would focus your attention. Those orthogonal phases is shown here, with a separation of non-steroidal anti-inflammatory drugs. Similar to before, this is a simple gradient run on all four columns. There is the PFP phase, the ECC18, the bonus RP, and the phenol hexyl. While the early eluters do not show much difference, the later peaks show many elution order changes. In this case, the Poroshell PFP gave the best resolution for all compounds. Also of note of those 12 reverse phase chemistries, 3 are designed for use at high pH. pH is a very powerful method development tool and can really change the selectivity and retention of ionizable compounds. On a reverse phase column, an analyte will have the best retention if it is not charged. If it is acidic, a lower pH will suppress the ionisation, and if they are basic compounds, you can either work in the mid-range, where you potentially have ionised the surface, creating a mixed mode effect. Or you can use a high pH stable Poroshell column at high pH and suppress the ionisation of the bases. Here you can see the same sample analysed at low and high pH. If you follow the arrows, you can see how the compounds move. The blue arrow indicates a basic compound which is more retained at high pH, and the red arrow marks an acidic compound which is more retained at low pH. There are also 3 neutral compounds in this sample, and as you can see they are unaffected by mobile phase pH. When developing a method, it's very worthwhile to optimise the selectivity by pH. Also, once you have settled on a pH, look at the separation a half of a pH unit higher and lower to make sure that selectivity is not lost, with slight variations in mobile phase preparation. Ideally, you want to be at least 1 to 2 pH units away from the pKa of the analytes to attain the robustness in the method. Speaking of robustness, be sure to use an appropriate column if working at high pH, such as the CsC18 or HPHC18 shown here. These phases are synthesized by chemically hybridizing the silica, resulting in a stronger, more robust particle, which allows for longer lifetime under these stressful chromatographic conditions. Another benefit to the wide variety of phases in the Poroshell 120 family is that you can also have multiple selectivity options to help you with method development at high pH, as shown here with the sample of pesticides. The CsC18 and HPHC18 give very different results with the same high pH method, and the HPHC8 is a third high pH selectivity option which is not pictured here. Of course, if you need to look beyond reverse phase separations, the Poroshell 120 family also offers 3 different helic chemistries. Unfortunately, we do not have time to discuss those today. However, if you'd like more information, please check out the application note listed in this slide. This note compares the usefulness of reverse phase versus helic options for polar compounds, as well as tips and tricks to ensure your helic separation is successful. And finally, the Poroshell 120 portfolio also includes 4 phases for chiral separations. We have a very detailed chiral application book. The publication number is referenced on this slide. Please check it out if you're interested in learning more about chiral separations and wish to see the extensive work that has already been done with these 4 phases. To sum up how to supercharge your method development, strive for a fast, simple method. Compatibility across a range of instrumentation is key, especially if you will need to transfer this method to another system in the future. Superficially porous particles on formic acid mobile phase can achieve this. And the InfinityLab Poroshell 120 CsC18 was made to excel under these conditions. And if additional method development is needed, don't forget the wide breadth of phases available on Poroshell particles, including high pH stable ones, as well as helic and chiral varieties as well. We focused on InfinityLab Poroshell columns today, but they are just one piece of the LC puzzle. You can rely on Agilent InfinityLab LC instruments, columns and supplies to deliver rugged, quality and robust analytical results. Every component of the Agilent Infinity family is uniquely designed to work together and to help you continuously improve your workflow. Thank you all for your time today. That brings me to the end of the presentation.